So chapter 18 is on DC circuits. DC stands for direct current. So we deal with two types of currents, direct current and alternating current. In this course, we're going to deal with direct current. So that's current that's traveling in one direction through a circuit. Okay, so it's not alternating, it's not moving back and forth. So our circuit's going to have one direction throughout the circuit, and if you're in lab, we've practiced drawing some circuit diagrams where we're familiar with some symbols a little bit based on a couple labs ago. So we're gonna get some more practice drawing circuit diagrams. So this is a picture of a battery and a resistor, right? Our light bulbs are they behave as resistors, so we're going to deal with resistors and capacitors in a circuit. So this is my symbol for a battery. Our convention is the longer line, the longer straight line it represents the positive end of the battery, and a resistor is kind of like a jagged line in a circuit, and a capacitor is two parallel lines equal in length to represent a set of parallel plates. So here are a couple of our circuit elements that we use in our diagrams. So a wire is just a straight line. Again, a resistor is our kind of squiggly, jagged looking line. We've got a symbol for a bulb, but since a bulb basically acts as a resistor, we're just going to use the resistor symbol for this chapter. Anytime a wire splits, if a wire ever splits and turns into two paths, we call this a junction. Alright, so and then we just draw our lines representing how the current or the wire splits into two, maybe three separate paths. And then we have a switch, right? A switch. We dealt with a switch a little bit in lab. An open switch means that no current can flow through it. If you close a switch, it basically just acts as a wire with negligible resistance. Technically, it's negligible, but in most cases we don't account for the resistance of the actual wire. I know in chapter 17 we were dealing with the resistive properties of metal wires, but for chapter 18 we're going to neglect the resistance inside wires. So an open switch has infinite resistance, basically, right? No current can flow through it, and a closed switch has no resistance and acts as a wire. So the first part of chapter 18 we're going to deal with capacitors, multiple capacitors in a circuit. So these diagrams show three capacitors, and they are joined in two different ways. So the diagram on the left, this represents three capacitors combined in parallel. Right? They're combined in parallel. And this diagram shows three capacitors that are in series. Okay, so any components that are in series, they're along the same path. Any capacitors in parallel, they are joined together by an initial wire, right? But then the wire is split, right? So the wire splits, and here's a junction, and then the wire splits in this case to three separate paths, and these components are on their own path. So this is what parallel components look like, and this is what series components look like. So let's just take two capacitors. What we're looking for in these circuits is we want to know what the battery senses, basically, right? What does the battery know is happening in this circuit? And so we're looking for the equivalent capacitance, right? The battery doesn't know how many capacitors or how many resistors are in the circuit. The battery is just going to behave based on the equivalent capacitance that is provided by the circuit. So we've got two parallel capacitors. If we go back to chapter 17 and chapter 16, when we look at the diagrams of a capacitor hooked up to a battery, we see that once the capacitor and the battery are in the same circuit and they're connected, the battery is going to push charges onto the plates of the capacitor, right? So one side is going to be charged positively, right? If we see this, that's connected to the positive end, right? Our electrons are going to be attracted to the positive end. So these two top plates are going to have a net positive charge, and then these two bottom plates are going to have a net negative charge because this negative end is going to be pushing the electrons onto the plate. Now, capacitors in parallel, if we have one capacitor, we see that over time the voltage across the capacitor is going to be the same as the battery. This applies to capacitors in parallel as well, right? So charge is going to be added to one side of the battery, charges are going to be taken away from, or the capacitor, I'm sorry, charges are going to be taken away from another side of the capacitor. And so the voltage across these two capacitors is the same as the voltage across the battery, right? So if this was a 9-volt battery, say, this was a 9-volt battery, the voltage across C1 would be 9 volts, and the voltage across C2 would be 9 volts. So they would have the same voltage. And so what we can do is we can draw this circuit, right? We can redraw this circuit as one capacitor with an equivalent capacitance of two capacitors in parallel. So our goal is to derive an expression for the equivalent capacitance that this battery recognizes. So charge is conserved, right? We don't really have a considerable amount of charge leaving a circuit. So the charge is conserved in this circuit. So what that means is the total charge on these two capacitors is the sum of the individual charges on these two capacitors, right? So they have their own unique charge, Q1 and Q2, but they have the same potential difference across them. So we're looking for an expression here for the equivalent capacitance, knowing that two capacitors in parallel, the sum of their charges is equal to the total charge, and then they share the same potential. So what I did, and I'll do this when we deal with resistors as well, is I took my equation for the charge on a capacitor, Q equals VC, and I rewrote this equation for capacitance and voltage. So these three expressions are going to come in handy. So what I like to do, just to kind of save myself from algebra mistakes, is I like to have these three equations written and handy. So I've got these capacitors in parallel, right? So I know the voltage across the first capacitor is equal to the voltage across the second capacitor, and those two voltages are equal to the battery. And then I know the sum of the charges on the capacitor is equal to the total charge. So what I'm going to do is I'm looking for an expression for the equivalent capacitance. So I'm going back up here and I'm using this equation right here, C equals Q over V. Alright, so let's say I know the total charge of the system and I know the voltage of the battery. So the total capacitance, the equivalent capacitance of that circuit, is Q total over the voltage of the battery. So I wrote this as Q total over V bat. But Q total is the sum of the charges of the two capacitors, so that's Q1 plus Q2. I can split this up into two fractions. So this is Q1 over the voltage of the battery plus Q2 of the voltage of the battery. But I know that the voltage on capacitor 1 is equal to the voltage on the capacitor 2, which is equal to the voltage of the battery. So I'm substituting V1 in for VBAT and V2 in for VBAT because they are equivalent. So Q1 over V1 is C1. Q2 over V2 is C2. So the equivalent capacitance of this circuit is the sum of C1 and C2. So if I have capacitors in parallel and I'm looking for the equivalent capacitance of that parallel capacitor system, all I have to do is add them up. So that's pretty nice. That's a pretty nice rule. For parallel capacitors, the equivalent capacitance is just the sum of the individual capacitance of each capacitor. Okay, so there's our first formula. So this is only for capacitors in parallel. Now let's go back and talk about capacitors in series. Right, we've got three. My example, I'm going to use two, but we've got three capacitors in series. So something different happens when we connect the capacitors in series. So charge is conserved, right? We've got a finite amount of charge. The positive end is going to pull electrons from here, right? And then the negative end is going to push electrons here. So this top plate of C1 is going to have a positive charge. And then the bottom plate of C2 is going to have a negative charge. What happens in between these two capacitors? So there's no change in charge here, right? But charge is going to move. Since this top plate is positive, it's going to attract all the negative charges that's in this region up to this negative plate. So then this is going to be negatively charged. Similarly for the bottom plate, right, it's got a net negative charge. So the negative charges are attracted to this plate and they are repelled from this plate. So this plate right here is going to have a net positive charge. So with capacitors in series, there's a voltage across capacitor 1 and capacitor 2. Their voltages add up to the voltage of the battery. So this is different from capacitors in parallel. The voltage across C1 plus the voltage across C2 is the voltage of the battery. Charge is conserved. There's a net positive charge here, a net negative charge here. There's no net negative there's no net charge in this location, but it's been displaced. So Q for C1 is equal to Q of C2. So they have the same Q. Okay, so that is Q total. Q1 plus Q2, or Q1 equals Q2, which is equal to Q total. Okay, so there's no change in charge in this system. So I'm going to use these two rules, the fact that C1 and C2 have the same charge and that their voltages add up to the voltage across the battery. I'm going to use those rules to derive an expression for the equivalent capacitance. So my rules go like this. The total charge is the charge on C1, and it's also equal to the charge on C2. The voltage of the battery is the sum of the voltages across each capacitor. So what I'm doing here, the easiest thing for me to do is to write an expression that is the voltage of the battery divided by the total charge. And the reason we do that is it's easier to split these fractions up like I did in the previous step. So I've got V over Q, but V over Q isn't C. V over Q is the reciprocal of C, or the inverse of C. Okay, so V over Q is 1 over C. All right. So the reason I do that is because I can split the denominator, right? Q total is Q1 is equal to Q2. So I'm doing similar algebra as I did in the other step, but I'm writing this as V over Q. So the voltage of the battery is the sum of the voltages across the capacitor, V1 plus V2. The denominator is still Q total, but that's equivalent to Q1 and equivalent to Q2. So I'm splitting this fraction up again. This is Q total, this is Q total. I'm substituting Q1 and Q2 in respectively. Okay, so this is the inverse of the capacitance of C1. This is the inverse of the capacitance of C2. So I've got my equation for the equivalent capacitance of capacitors in series. Now this is written a little bit differently, right? This is equivalent capacitance is 1 over C1 plus 1 over C2 plus 1 over C3 all to the -1. Okay, so this is basically 1 over everything that's in parentheses. The way I like to write it makes it easier for me to remember how to solve for the equivalent capacitance, how to calculate it. So I like to write it like this. 1 over the equivalent capacitance is 1 over C1 plus 1 over C2 plus 1 over C sub n for any capacitors, any number of capacitors in series. Okay. Now the reason I write it like this is because when I add up these fractions, right, when I add up these 1 over C's, I'm going to be left with farads in the denominator, right? And that's going to remind me that I have to flip the fraction, right? And this is a common thing. We tend to forget this a lot. I have to flip the fraction. So once I add all of these, I still have the inverse of the equivalent capacitance, right? So once you add up all these fractions, we're going to take the reciprocal of that, and that's going to give us our equivalent capacitance. And I'll just show you my technique in the first example, just to kind of remind myself that I have to do this each time. Okay, so this is all raised to the -1 power. So we're adding up the inverses of the individual capacitances, and then we're taking the inverse of that value. So I've got a sample circuit here. I'm going to set up my strategy the way I learned it back when I took physics so many years ago. I'll show you my strategy. Maybe a little tedious at times. You may feel like it's a few unnecessary steps, but this is the practice that I like to have to avoid mistakes. So in this diagram, I've got a 12-volt battery that's connected to 3 capacitors. So I've got a 4 microfarad capacitor, that's 10 to the -6, 2 microfarad capacitor, and a 3 microfarad capacitor. So the first thing I notice, I like to use this as my first example, is the first thing I notice is I have 2 capacitors in parallel. So I've got these 2 capacitors in parallel. But this 2 capacitor system is in series with this capacitor. So what I want to do is I want all of my diagrams to look like this. I want all of my diagrams to look like this. 1 battery, 1 capacitor with an equivalent capacitance. And my physics teacher called this collapsing the circuit. Right? So I'm going to use these 2 rules that we just established. I'm going to use these 2 rules to add capacitors together and then reduce the circuit to 1 battery and 1 capacitor. So that's my goal here. Okay, I want to reduce this to an equivalent capacitance. The first thing I'm going to do is I'm going to look for 2 or more capacitors that are directly connected either in series or parallel. Now when I look at this diagram, I see that the 4 microfarad capacitor and the 2 microfarad are directly connected in parallel. Okay, so what I can do is I can add these 2 capacitors and find their equivalent capacitance. Every time I add capacitors, whether in series or parallel, I like to redraw the circuit. And the reason I like to redraw the circuit is because in order to find the charge on and the voltage drop across each capacitor, I like to go backwards, and I have to look at each step of my circuit collapsing and use Q equals VC to find these values for each capacitor. Alright, so let's tackle step 1 first. We're looking for the equivalent capacitance of the circuit. So the 4 microfarad and the 2 microfarad capacitors are in parallel, so those I can just add. Right? I can just add. I don't have any reciprocal rule for capacitors in parallel. So 4 plus 2 is 6 microfarads. So I'm redrawing the circuit. Right? I'm redrawing the circuit because I want to refer back to this diagram for step 2. So I'm redrawing this, but instead of having the 4 and the 2 in parallel, I just redraw this as one 6 microfarad capacitor. So now I notice that I've got a 6 microfarad capacitor and a 3 microfarad capacitor in series. So now this is my reciprocal rule. So I'm looking for the equivalent capacitance of the 6 and the 3. So 1 over the equivalent capacitance is 1 over 6 microfarads plus 1 over 3 microfarads. So what I'm going to do here first, and I don't do this every time, but for the first example I like to do this. I'm going to factor out my units. Okay, I've got microfarads in the denominator, so I'm factoring out my units from both of these terms. So now I've got 2 fractions. All right, if you're a common denominator person, go ahead and find the common denominator. I like to do this trick where I multiply these two together. Right, 3 times 1 is 3, plus the product of these two. 1 times 6 is 6. Right, divided by the product of the denominators, 18. Okay, so that's a little trick I learned a long time ago, because I always mess up common denominators for some reason. So I'm adding these 2 fractions together. I get 9 over 18, which is 1 over 2. But what happens is, as I'm doing this, I still have microfarads in the denominator. And the reason I factored this out is to remind myself that my units are in the denominator, right? And so I'm looking for capacitance, and so microfarads has to be in the numerator for the equivalent capacitance. So that reminds me that I have to flip this fraction at the very end, right? Because this whole process right here, I was solving for 1 over the equivalent capacitance. So when I flip this fraction, I get 2 microfarads for the equivalent capacitance of the entire circuit. Okay. So here's the end of step 1. The end of step 1 is a diagram with a battery and a capacitor that represents the equivalent capacitance of the entire circuit. So that's step 1 right there. 2 microfarads is the equivalent capacitance. Once I get to this point, I'm starting step 2, which is find the charge and the voltage on each capacitor. So I've got 3 capacitors. I've got to find Q and V for all 3 of those. Now this depends on me remembering the rules for series and capacitor circuits. So I'm down here. The first thing I'm going to do, I've got a battery with a voltage, I've got a capacitor with a capacitance. That means I can find the total charge of the circuit, Q total. Okay, find the Q total. That's the voltage of the battery times the equivalent capacitance. So I've got 12 volts times 2 microfarads. That's 24 microcoulombs. Okay, so this is Q total, right? That's the total charge on all of my capacitors. Now I'm going to go backwards. I'm going to expand the circuit, and every step of my expansion I'm going to use my rules, and I'm going to find Q and V for each capacitor. So let's expand. I like to redraw them again. Again, like I said, it may seem a little redundant, but I like to be careful. All right. So we're using Q equals VC and our voltage and charge rules to find Q and V on each capacitor. So I go back one step, right? I split it back up into the 6 microfarad and the 3 microfarad capacitor. 2 capacitors in series have the same charge on them, and the sum of their voltages is equal to the voltage of the battery. So with this, I've got a couple values that I know and an equation that I can write. So the voltage of the battery is the voltage across the 6 plus the voltage across the 3. The charge on each capacitor is equal to Q total. Right? It's equal to Q total, which is 24 microcoulombs. So in this step, I can say Q6 is 24 microcoulombs, Q3 is 24 microcoulombs. And then this equation is true. right? But I know the voltage of the battery, but I don't know V6 or V3. So I'm going to solve for V6 and V3. So V6 is Q total, which is also Q6, 24 microcoulombs, divided by its capacitance. I'm going to go all the way back up because that's why I wrote these three variations of my equation, because I like to have this handy. V equals Q over C. Alright, so I'm looking for V6 and I'm looking for V3. I know Q6 and I know Q3 from my rules, so I'm looking for V6 and V3. So Q6 is 24 microcoulombs, C6, the capacitance of this capacitor, 6 microfarads. That's 4 volts. So what you'll see often is our capacitances and our charges are usually the same order of magnitude. Okay, so I'm not really calculating 24 times 10 to the negative 6 divided by 6 times 10 to the negative 6. I'm basically just canceling out the 10 to the negative 6. I'm canceling out the micros. Okay, so I have 24 divided by 6 and I have 4 volts. So I have the same thing for V3. I know the charge on V3, or I know the charge on the 3 microfarad capacitor, and I know its capacitance. So 24 microcoulombs divided by 3 microfarads is 8 volts. So before I go any further, I just want to make sure that I'm doing everything correctly. So I'm just going to check, right? Is the voltage across the 6 and the voltage across the 3, do they add up to the voltage across the battery? And that's true. 4 volts plus 8 volts is 12 volts. Okay, so I'm doing good so far. Everything looks good, same charge, I'm following the rules. The voltages add up to the voltage of the battery. So I'm going to expand one more step. So I'm expanding the 4 and the 2 microfarad capacitor to, or I'm expanding that 6 microfarad capacitor back to the 4 and the 2. Now, capacitors in parallel have the same voltage across them, and the sum of their charges are going to equal the total charge across the equivalent capacitor. But I'm dealing with a part of the circuit, right? Not the entire circuit anymore. I'm dealing with a part of the circuit. So when I'm dealing with the 4 and the 2, my values have to match what was true for the 6. All right. So the capacitance of the 6 microfarad is 6 capacitor, 6 microfarads. The voltage across the 6 microfarad capacitor was 4 volts. All right. So I'm going to use that. And the charge on the 6 microfarad capacitor is 24 microcoulombs. So when I'm dealing with these two capacitors, I'm going to use 4 volts for the voltage and 24 microcoulombs for the charge. They're in parallel, they're going to have the same voltage across them. So that means the voltage across the 4 is equal to the voltage across the 2, which is 4 volts. Alright, so be very careful. Don't use the voltage of the battery. We're going to use the voltage across the 6 microfarad capacitor. So Q4 plus Q2 is going to equal Q6. They're two capacitors in parallel. Their charges are going to add up to Q6. What's Q6? 24 microcoulombs. So I'm using Q equals VC. Since I know that the voltage across both of these capacitors is 4 volts, I'm going to use Q equals VC to find the charges on each individual capacitor. So I use 4 volts for the voltage, 4 microfarads for this capacitor's capacitance, and I get 16 microcoulombs. Same thing for the 2. The voltage is also 4 volts. Its capacitance is 2 microfarads. So 4 times 2 is 8 microcoulombs. Again, I've got 1 micro, so I'm dealing with microcoulombs. Right? A volt times a farad is a coulomb. A volt times a microfarad is a microcoulomb. So I'm going to check my work. I'm going to make sure that the sum of these two charges equals the total charge across my 6 microfarad capacitor. 16 plus 8 is 24. The rules match. I did everything correctly. Okay. So a simple start, right? 2 in parallel. When you collapse them, you have 2 in series. So this is a good example of using both of the rules for capacitors in series and capacitors in parallel. So we've got 4 capacitors in this example. We've got a 90-volt battery, and we've got 4 capacitors, a 3, a 6, and a 2 and a 4. So it looks kind of hectic, right? It looks a little crazy, but I'm just going to go through the same rules, right? I'm looking for the equivalent capacitance first. I'm going to collapse the circuit, find the equivalent capacitance, add up the capacitors. But what's interesting about this is I'm trying to look for 2 or more capacitors that are directly connected in series or parallel. And so what I notice is that the 3 and the 6 are directly in series with each other. Right? They're both along the same path right here. So I can add these 2 together in series. I can do the same thing for the 2 and the 4. They're on the same path, even though they're inside this, weird parallel junction looking thing. They're directly in series with each other, so I can add them as the first step. So I'm going to add the 3 and the 6, and then I'm going to add the 2 and the 4, and again I'm going to redraw my circuit just to keep track of all my steps. So the 3 and the 6 are in series. I'm going to use the reciprocal rule for capacitors because they're in series. So 1 over the 3 microfarad plus 1 over 6 microfarads is 6 plus 3 over 18. I'm using that fraction adding trick. So I get 9 over 18. I'm keeping the microfarads in the denominator again. And so I get 1 over 2 microfarads. Can't forget to flip, right? Can't forget to flip because I'm looking for the equivalent capacitance. And that's 2 microfarads. So I'm going to do the same thing for the 2 and the 4. Now this is going to get a little tricky because I've got a 2 microfarad capacitor here, but these 2 capacitors have an equivalent capacitance of 2 microfarads. So I'm gonna rename them, hopefully eliminate that confusion. So these 2 capacitors are in series. I'm going to add them up the same way. 1 over 2 microfarads plus 1 over 4 microfarads is 6 over 8 microfarads, which is 3 over 4 microfarads. Don't forget to flip 4/3 microfarads. So I like to keep my stuff in fractions, not really turn them into decimals. I don't like fractions or decimals, but I prefer fractions because something might cancel, right? I'm going to use this number throughout the problem. I'm going to use this value, and so maybe something will come out nice and cancel this 3. So I'm okay with just keeping this as a fractional value. So I'm redrawing the circuit. Here it is. The top path has an equivalent capacitance of 2 microfarads. The bottom path has an equivalent of 4/3 microfarads. Now in this diagram, these 2 new capacitors are in parallel. So all I have to do is add them up. 2 plus 4/3 is 6/3 plus 4/3, and so I get 10/3 microfarads. That's the equivalent capacitance of the entire circuit. So just like the previous example, I've finished step 1. I've redrawn my circuit to look like 1 battery and 1 capacitor with an equivalent capacitance of 10/3 microfarads. So now I'm ready to use Q equals VC to find the total charge on the capacitors. Voltage of the battery is 90 volts. Capacitance is 10/3 microfarads. Again, that's why I use the fraction, because the 90 and the 3 reduce. I get 30 times 10, 300 microcoulombs. 300 microcoulombs. Again, I'm just bringing the micros along with me. I know it means 10 to the negative 6. So rather than trying to deal with big numbers or powers of 10, I'm just carrying it along with me. Okay. So I've got my equivalent capacitance. I've got the total charge. Now I have to expand my circuit. I have to go backwards again and find the voltage drop and the charge on each capacitor. So in this process of my expansion, so I go back to the 2 and the 4/3, but I don't want to confuse this 2 with this 2. So what I'm going to do is I'm going to call this capacitor A, and I'm going to call this capacitor B. Alright, so this is capacitor A, capacitor B. I've got 2 capacitors in parallel. Excuse me. They've got the same voltage across them, which is the voltage of the battery, 90 volts. So I know the voltage across capacitor A, capacitor B. They have their own unique capacitance, so they're going to have their own unique charge on them. So I use Q equals VC for both. So the charge on capacitor A is 180 microcoulombs. The charge on capacitor B, 90 volts times 4/3 microfarads, I get 120 microcoulombs. So every time I find either the individual charge on 2 capacitors or the voltage across each capacitor, I'm going to add them up and make sure that they add up to the equivalent charge or the equivalent voltage. So they add up to 300 microcoulombs. So that's good, right? So these two, the charge of across these 2 capacitors is equal to the charge on this equivalent capacitor, 300 microcoulombs. So every step I'm checking my work to make sure, you know, I did my math right and I applied my rules correctly. So now I'm cheating a little bit, but I'm splitting capacitor A and capacitor B, right? So I'm kind of doing 2 steps in this expansion because, you know, I did the same thing here, right? So I added them up and added them up in 1 step. So I'm expanding them, right? Capacitor A, I'm splitting it back up to the 3 and the 6. Capacitor B, I'm splitting it back up into the 2 and the 4. Now capacitors in series have the same charge on them. Their voltage drops are going to be different. So the 3 and the 6 have the same charge on them as capacitor A. So I'm going to use 180 microcoulombs for the charge on the 3 microfarad and the charge on the 6 microfarad. So Q3 equals Q6 equals QA equals 180 microcoulombs. Similarly for the 2 and the 4, their charge is equal to the charge on capacitor B, which is 120 microcoulombs, right? So notice again, I'm not using 300, I'm not using the charge on all the capacitors, I'm using the charge on A and the charge on B for these individual capacitors. They have their own capacitance. I'm going to go back up, all the way back up to my equation for voltage. So I'm going to find Q over C, which is the voltage for all 3, or excuse me, all 4 in this case, right? All 4 of these capacitors. So the voltage across the 3 microfarad is Q3 over C3. Calculate that. My micros go away. 180 divided by 3 is 60 volts. Voltage across the 6 is Q6 over C6. Same charge divided by its capacitance. Again, micros go away. 180 over 6 is 30. I'm going to add these 2 up, and what do I get? 90 volts, which is the voltage across the battery. Okay, the voltage across the battery. Because remember, the voltage across A is a voltage across B is a voltage across the battery. So their voltage drops add up to 90 volts. So I'm doing a good job so far. I'm going to do the same thing with the 2 and the 4. I've got Q2 over C2. I'm using 120 microcoulombs divided by its capacitance, 2 microfarads. I get 60 volts. Voltage across the 4 is Q4 over C4. 120 microcoulombs over 4 microfarads is 30 volts. Right? So we might be seeing a little bit of a relationship here, right? The proportions between, you know, capacitance and their respective voltages. Again, the 2 and the 4 also add up to 90 volts, which is the voltage across my B capacitor, right? This one right here. 90 volts, 90 volts. Their voltages add up to 90, their voltages add up to 90, right? So I'm always checking my work with each step to make sure that I applied my rules correctly, okay? So the next video I'm going to start with resistors. The rules are going to be very similar, but we're going to apply them a bit differently, and we're going to use Ohm's law instead of my charge equation, okay? Because charge actually flows through resistors, it doesn't get stored on the resistors like they do capacitors, okay? So in my next video, I'll finish up chapter 18. Also, I think I made a news item on D2L, but I have many other example circuits. So I tried to find as many example capacitor and resistor circuits that I thought were reasonable and practical to do in preparation for the exam. So go ahead and check them out. I've got a document that has the capacitors, the capacitor circuits and the resistor circuits, and then I have two sets of solutions, two documents. One document is the solutions for the capacitor circuits, and then the other is the resistor circuits. So try to solve those capacitor circuits on your own as best you can. Try not to peek at the solutions. That'll get you some good practice, help you practice applying the rules, adding up, equivalent capacitances, finding the charge, the voltage, all that stuff. Okay? So next video I'm going to start with resistors. Alright, thanks.